For this example, we're asked to look at a system having 2 degrees of freedom. We have particles 1 and 2 interconnected by springs and dashpots that are as shown. x1 and x2 represent the absolute motion of blocks 1 and 2. In addition, we have a harmonically varying force, F0 sine omega t, which is acting at particle 1. What we want to determine is a steady state response for the coordinates of x1 and x2 due to this harmonic excitation. As always, we'll start out by deriving our equations of motion. Again, we need to write things in terms of x1 and x2. x1 and x2 are absolutes, so this is 1/2 mx1 dot squared plus 1/2 mx2 dot squared. Potential. The spring on the left is 1/2 k x1 squared. The potential for the spring between 1 and 2 is going to be x2 minus x1 quantity squared. The Rayleigh dissipation function, very similar in form to u, that's 1/2 c x1 dot squared plus 1/2 c x2 dot minus x1 dot quantity squared. So based on our results that we have from Lagrange's equations, looking at the linearized form of the equations of motion, we know that this ends up being m11. This becomes m22. There's no cross terms, so by inspection our mass matrix looks like this. The C matrix. The C matrix, as we know, is the mixed partial of R with respect to the x dots evaluated at the equilibrium state. In that case, our C matrix becomes 2C minus C minus C and C. Same kind of thing with our stiffness matrix K. We do the mixed partials of the potential term with respect to the x's, evaluated at the equilibrium state. So the K matrix becomes 2K minus K minus K and K. We need to find our differential work. Differential work will be, we look at the force. The force is acting in the x direction. It's acting at particle 1. So the differential change in position for particle 1 is simply going to be dx1 in the I. So we see that this differential work is F dx1. So this is our Q1. In Q2, since there's no dx2 which is appearing, we say that dx, or Q2 there, is a 0. From this, we know that we can write down our equations of motion. Equations of motion become mx double dot, where x is x1 plus x2 in a column vector, c times x dot plus k times x, where the right-hand side is f0 0 sine omega t, like this. And what I will do is refer to this as being an amplitude vector there of capital F0. Keep in mind that this here is the same thing as F0 times the imaginary part. It looks like I don't have space here, so let me write it down here. F0 as a vector times the imaginary part of the complex exponential. Our solution. Well, if we look at it from the perspective of the complex exponential, what we need to do is put in a particular solution for x as being the solution or amplitude vector there of x times ei omega t. And again, since the right-hand side is the imaginary part of that, we will take the imaginary part of that result. So the solution, the particular part, as we just said here, is equal to the imaginary part of a vector here x times e I omega t as that. The way we find x is we substitute this first back into our equation of motion. So we substitute this into the equations of motion that we have, and that becomes m with a minus omega squared in front plus I times omega times c plus k x is equal to f naught. So from this we know that the vector x, the solution vector x, we take the inverse of the matrix here of minus omega squared m plus I omega c plus k. We invert that. It's going to be a 2 by 2. It's going to be complex, but yet it's going to be a 2 by 2. Post multiply that by f naught. So I'm going to write this out. This 2 by 2 is going to be minus m omega squared plus 2k. That's the real part of the 1, 1 position. We have 2 omega c times I in that position. Over here in the 2, 2, let me write that one out, minus m omega squared plus k plus omega c times I. The 1, 2 position is minus c omega I minus k. And of course this is symmetrical, so this is minus c omega I minus k. Invert that, and f naught we call as a vector is the scalar there of f naught. In the first position divided, or in the second slot there is a 0. So in general, what we need to do is invert that 2 by 2. We need to multiply it through, and that gives us x. Multiply x by e I omega t, and extract out of there the imaginary part. What I want to do first is look at the undamped case. We can learn a lot about the response when looking at the undamped case, and it's far less cumbersome in terms of algebra than when damping is involved. And then we'll come back and use MATLAB to help us make the plots when we have damping in there. So for the undamped case, we basically pull out the imaginary parts. So this is minus omega squared plus 2k, a minus k, a minus k, minus m omega squared plus k inverse f naught in a 0. Usually the inversion of a matrix is a very complicated thing when you're doing it by hand, but for a 2 by 2 it's actually fairly easy to do. One thing you do is you divide everything through by the determinant, which I'll write down in just a bit. But what you do is you switch the positions of 1, 1 and the 2, 2. This is minus m omega squared plus k, minus m omega squared plus 2k. And then you take the off-diagonal terms and simply change their sign, S-I-G-N sign. The details on inverting a matrix is given back in the appendix of the notes, and what you'll see there is an expression in terms of these cofactor matrices. But again, for the 2 by 2, it's as basic as what we just wrote down here. So I need to multiply that through by that forcing vector f naught. So whenever I do that, what I end up with is in the 1, 1 position, I get minus m omega squared plus k K in the second slot, and there's going to be an F naught over that, where, as I mentioned before, the delta is the determinant of the minus omega squared m plus k. And when I expand out that, I get minus m omega squared plus 2k minus m omega squared plus k minus k squared. And expanding this out, it becomes m squared omega to the fourth minus 3 mk omega squared plus k squared. So a few things that we can observe from our response. This is for, again, the undamped case. So the observations that we can make is, one, is that if we set delta equal to a 0, what we've got is the characteristic equation. Recall that the characteristic equation is what you solve to get the natural frequencies. So if I solve that, what I'm going to do here is I'm going to find the values of omega that make the natural frequencies of the values of omega that make the denominator as a 0. So therefore, it says that when omega is equal to the first natural frequency, omega 1, if omega is equal to the second natural frequency, omega 2, one of those two situations produces a situation where delta is a 0, which implies that x1 and x2 are unbounded. And in some sense, that's not totally unexpected, because when we excite this system at a natural frequency, we get a resonance. It just happens for 2 degrees of freedom. We have 2 of them, where before a resonance for a single degree of freedom, that was only 1. And recall that from what we've done before, we can find the natural frequencies. The natural frequencies are, at least the square of them, is equal to 3 plus or minus the square root of 5 over 2 times k over m. So those are the frequencies that we look for. Omega going to a 0. Omega goes to a 0. What we have, if you look back at our solution above, we end up with 1, 1, f naught over k. So this is the static deformation. Static deformation means that if F were a constant force applied in a very slow way, that's the deformation we would get. The block on the left would deflect by F naught over K. The block on the right would move the same as the block on the left, so they're both equal to F naught over K. The other extreme, when omega is large at high frequency, if you look back at our expressions, they both go to a 0. But please note that the other one, the one position goes to a 0 from the negative side, and 2 goes to 0 from the plus side. And the last observation is an interesting one, I think, is that when omega is equal to the square root of k over m, what we have is x1 ends up being a 0, and I'm not sure what x2 is, but it's not a 0. So it turns out that at that excitation, the block on which we apply the force is at rest, yet block 2 is moving. Interesting result, I think. But what I'm going to do is use those results to make a plot of x1 and x2. So this is going to be the axis there for x1. This is going to be the axis there for x2. And there's a couple frequencies, actually 3 of them, we're going to denote with lines. That's the first one's going to be omega 1. The next one is going to be when omega is equal to the square root of k over m. That's going to be this line here. And the last one is going to be when omega is equal to the second natural frequency there of omega 2. So again, I'm plotting x1 and x2 here. Omega, omega. And so the response starts out here at f0 over k for low frequency. It goes like this. It passes through here like this. And it ends up like that. Again, it goes small on the right-hand side from the negative side. We see that from the equation. x2 also starts out at f0 over k. It has a resonance here at omega 1. It comes up from the bottom, but please note that it doesn't cross. It actually comes back down like this, and then this curve then comes in from the top. It approaches a 0 there on the right-hand side from the plus sign. So again, our important frequencies here are omega equal to omega 1 equal to omega 2, our 2 resonances. Square root of k over m is important because that's where x1 is a 0. What I'm going to do is put it in a more standard form by taking the absolute value of those. So that's what the plot is going to be used for there in the book. This is f0 over k. I take the absolute value of what I just drew. Comes down to a cusp here. Comes back up simply because I'm taking the absolute value, and it goes down like that. x2 looks a lot like that, except please note between omega 1 and omega 2, it doesn't come all the way down. It turns and goes back and looks like that. So this frequency, again, is omega 1. This is omega 2. And this is at square root of k over m. The names that we give to these things, these values at which the undamped response is unbounded, just like it was for the single degree of freedom case, those are our resonances. Wherever we have an amplitude going to a 0, that's called an anti-resonance. Later on, when we look at vibration absorption there in chapter 5, we're going to take advantage of that, because that's a place where the response of particle 1 is as small as it's going to get. So in a design, if this is the design of a system of interest, you would like to place that anti-resonance at a frequency where before there may have been large amplitude response. If you could move it to an anti-resonance, you will have greatly improved the response. If we now look at the damped case, use MATLAB. And use MATLAB to first invert this matrix. That was times f0. And then we would say that xp of t is going to be the imaginary part of x times e I omega t, like that. What you're going to find is when you plot the magnitude of x1, it's going to look something like this. For some light value of damping, you're going to find that the response is going to look like this. doing a lot of what you would expect. Near a resonance, it brings the amplitude down. It controls the a resonance. Same way here for X2. It likely would look something like that. And the rate at which the peaks come down depend a lot on the exact parameters that we have in terms of C and M and K. But an interesting point, which we will come back and talk about a bit in Chapter 5, is note that the undamped case at the anti-resonance had zero amplitude. By putting damping in the system, we actually raised the amplitude response at the anti-resonance. So damping in this case, if you're trying to reduce the amplitude of response, it doesn't work. Damping actually makes things worse. Anyway, long example here, but the problem is, just like we have for single degree of freedom, we drive the equations of motion, we look for the steady state response either through harmonic balance approach of assuming a solution of cosines and sine, or as we did here, using the complex exponential approach to get the amplitude of response. Along the way, we discovered the idea of resonances for multi-degree of freedom's system. The system having 2 degrees of freedom, it has 2 resonances. It also introduced the idea of an anti-resonance. In this case, X1 has an anti-resonance, only one. X2 has none. The problem by problem thing in terms of the number of anti-resonances that you'll have for any given coordinate in a problem. However, the number of resonances will always be equal to the number of degrees of freedom that you've got.